Okay, now that we've formulated our basic finite difference equation using either approximation of derivatives or Darcy's law of conservation of mass, we now need to consider boundary conditions. And so let's talk about that. If we have known head at a boundary, like if we're on one of the nodes that's on a boundary and it's a fixed head, a constant head boundary, we basically set the head equal to that known head value, and that becomes the equation for that node. There's nothing to solve for, we already know it. And then we use that head when it's referenced by other adjacent nodes where the head is unknown. Okay, so that's the easiest kind of boundary condition. Things get a little more complicated where you have no-flow boundaries. So we're going to look at each of the different possibilities for no-flow boundaries. Now, the first case we're going to look at is we have a node that's adjacent to an impermeable boundary. So we have a node on the left, the node on the right, a node below, but nothing above. And so since it's a no-flow boundary, we know that there's no flow in the y direction, so qy is equal to 0. And therefore, we can also say that if the flow in the y direction is equal to 0, the hydraulic gradient in the y direction is equal to 0. Therefore, what we do is we create an imaginary node A up an equal distance above, delta y above. And then if we assume that the head at A is equal to the head at B, then the hydraulic gradient in the y direction is 0. There's no change. The delta H is 0. Therefore, if we go back to our original equation, and this is the simplest version of it that has delta x equal delta y, if we simply substitute H sub B for A, and H sub B is, H sub A is equal to H sub B, so we end up with 2HB here. This is the proper equation for that node. So for nodes on an impermeable boundary, you just use 2 times the head in the pervious region, and then you put that in the equation, and you ignore the other missing node. And that's it. It's just like a super simple case. What if we have flow on an inside corner? So we have an impermeable material all the way around here. This is shown as white, but just consider that to be impermeable all the way around. In this case, we do the same kind of thing, but instead of creating one imaginary node, we do 2 imaginary nodes, one at A and one at R. And we assume that the flow in the y direction is 0. It's a no-flow boundary, so the hydraulic gradient in the y direction is 0. That's actually in this direction. And then we say that the same thing in the x direction. So we apply the same 0 hydraulic gradient condition in both cases. And if the hydraulic gradient in the vertical direction is 0, that means H sub A is equal to H sub B. Delta H is 0. And in the horizontal direction, HL is equal to HR. So now if we go back to our original equation and substitute HB for HA and HL for HR, again we're using the simple form of the equation that has delta X equal delta Y, then we have H sub I is equal to 1/4 2 times HL plus 2 times HB, or 1/2 HL plus HB. So again, we go back to here. For node I, we get 1/2 of node L plus 1/2 of node B. And that's it. That's our governing equation. Again, it ends up being something that's really simple. And now let's look at an outside corner. So we have this is impermeable, and we have water flowing around this outside corner. In this case, we can't use imaginary nodes, and we can't say that the flow in either the horizontal direction or the vertical direction is 0, because it's not. What we can say is that in the flow in the x direction, on this side it's going through a smaller space, going to a bigger space, and on the y direction it comes in through this big space and goes out through this small space. And therefore, instead of using a finite or just simply substituting imaginary nodes in the equation, we're going to do this one using Darcy's law. And so the flow in is the q left plus q bottom. So the flow, the flow into this is this flow plus this flow. And to get the Darcy's law here, we're going to, the area that it flows through is going to be 1/2 of delta y. So notice we have a delta y over 2. And then in the x direction, it's a full delta x because it's this flow that's going out the right side. And then in the vertical direction, we have an entire delta y that delta x that it flows through going in, but going out, it goes through a 1/2 delta x. And so yeah, excuse me, I'm doing this wrong. The flow out, the flow in is this one plus this one. The flow out is this one plus this one. So the flow out is qx over this entire delta y, and the flow out is qy, which is applied over 1/2 of the delta x. So here's the term going out the right side. Here's the term going out the top. Again, same thing we had before in our formulation number 2, but we have delta y over 2 and delta x over 2. If you apply conservation of mass and set those equal to one another, and if you assume kx equal ky and delta x equals delta y, the equation simplifies to this, which 1/2 h sub l plus hb plus hr plus 1/2 h sub a over 3. So let's go back to this equation. So it's 1/2, so the head at node I is 1/2 of the head here, plus 1/2 of the head here, plus all of the head here, plus all of the head here, divided by 3. So again, it ends up being a pretty simple equation. Now that we've considered all those cases, it turns out we can generalize this a little bit. There's a simple algorithm you can use for any no-flow boundary, for any combination of impervious quadrants. 2 impervious quadrants, 1, 3, you don't do 4, of course, so it's either 1, 2, or 3. So basically what we do is we look at node I, and we multiply each of the nodes by 1/2 times the number of pervious quadrants adjacent to the node, and then divide by the total number of pervious quadrants. So imagine that this top half is impermeable. We would say 1/2 of HL plus 1/2 of HR plus all of HB divided by 2. And that would be our equation that we derived earlier. Or if we have 3 impervious quadrants, these 3 here, we would say 1/2 of HL plus 1/2 of HB divided by 1, because there's only one pervious quadrant. And the other case is the one we just saw. Let's suppose this quadrant up here is impervious. We do 1/2 of A, 1/2 of R, all of B, all of L, divided by 3. So again, here's another graphical representation of this. All of HL, 1/2 of B, 1/2 of R, all of A, minus 3HI equals 0. Solve for H. Again, this is what we want to jump right to. So all of L, 1/2 of B, 1/2 of R, all of A divided by 3. 1, 2, 3 quadrants. Now, if we can just remember that simple rule, we can formulate an equation for any node on an impervious boundary. All right, so what do we do if we have a sheet pile? Well, if you have a sheet pile that penetrates down, that represents a no-flow boundary that penetrates into the grid. So what you do for a mesh-centered grid is you basically split your grid so you have a node on the left and the right side of the sheet pile, and then there's a node down here. So let's look at node A for a second. If we were to formulate the equation there, that would be an impervious boundary with two pervious quadrants. So it would be 1/2 of this, all of this, 1/2 of that divided by 2. And likewise, this one up here, it's a known head condition. But what about this one up here? It's in a corner. So you do 1/2 of this one plus 1/2 of this one divided by 1. Now, and then here you do 1/2 of this head, all of this head, 1/2 of this head divided by 2. And down here it gets a little more interesting. We now have 4 pervious quadrants, but what we do is we say we take 1/2 of A, 1/2 of A prime, all of L, all of B, all of R, and we divide by 4. So this is kind of a special case, that node right there at the tip of the sheet pile. But it still follows the same pattern that we derived earlier. All right, so let's suppose we had our classic sheet pile problem with these dimensions. It turns out that you can formulate these equations and solve them inside like Fortran or Python or some programming language. If you assume kx is equal to ky, and if you use uniform spacing, the equations are so simple you can actually solve this using a spreadsheet. And so what you do is you set up a grid, looks something like this. We have a sheet pile down the middle, so we can formulate our equations for those like we did before. These nodes, 5 nodes right here, are specified head. This is an impervious boundary. Over here on the right, this is a known head value. Down this side, we're going to assume on the bottom all the way around, it's no flow boundary. And then everything in the middle is just the general case. So this head is equal to this plus this plus this plus this divided by 4. And so what you do is you can set up a spreadsheet. This is one we'll be doing together in class. And we've merged the cells underneath the sheet pile. And so we have a cell in our spreadsheet for each of these red dots. So again, each red dot becomes a cell. So you'll notice that we have 1, 2, 3, 4, 5 here. 1, 2, 3, 4, 5. So this cell right here is the one right at the tip of that clay blanket. So these are a boundary condition. We just put the number in there of the upstream boundary condition, and these along here have the downstream boundary condition. And then all of the other boundaries are no flow, and everything in the middle is just a general equation. So we end up, you go into each of these cells and you just say the head at this cell is equal to this plus this plus this plus this divided by 4. And you copy that everywhere. And what happens is you end up getting, so you have an equation for all of these, but you end up with circular equations because the equation for this cell here references the one on the right, and the equation for the one on the right references this one here. So you end up having circular references, and so you have to, there's an option in Excel to do an iterative solution. So it's useful when you have circular equations which will eventually converge. And so I'll show you how to do that in our exercise, but you can actually solve a pretty broad variety of problems using the finite difference method in Excel, which will be the primary method that we'll use to solve finite difference this semester.